Good afternoon, everyone. It's my pleasure today to introduce Sauvik, who works at the intersection of HCI and computer security. And he has won a Best Paper Award at UbiComp and 2 honorable mentions at CHI, and an honorable mention for the NSA Best Scientific Cybersecurity Paper Award. And he's also won a bunch of fellowships, including the Facebook Fellowship and the NDSEG Fellowship. And he will be telling us today about his work. And with that, I'll let you take it away.
Thanks, Francie. I was a finalist for the Facebook Fellowship, actually, just not to, not to spread any misinformation there. Also, you are safe, even though I did get that NSA award. Not affiliated with them in any way, so don't worry. So I'm excited to be here, and I wanted to start with a question, which is, how can we design systems that encourage better cybersecurity behaviors? Now, this is a question that has driven a lot of my own PhD work, and I think it's an important question to engage with because of how foundational security is to many of the computing services we sort of use and enjoy today. Things like mobile banking, communicating with our friends and loved ones online through email and messaging applications, and creating and sharing intellectual work. All of these things, security is pretty foundational to them. So it's also no surprise that the exploitation of weak security behaviors remains sort of a massive enterprise. One IBM estimate puts it at $445 billion a year, with professional cybercrime units suiting up and producing upwards of 250,000 new pieces of malware every single day. Malware like the direwolf, which sends unsuspecting users emails that look like they've come from their friends in order to get them to install malware, which steals their banking credential information, takes money out of their account, and then DDoSes the user's home network so that the users don't know what hit them or what to do about it. And the kicker is that much of the cybercrime industry and most of the sort of malware that they produce could be hamstrung if end users, use recommended expert security practices, things like keeping their software fully up to date, using two-factor authentication on important accounts. And yet, when we think of security in the end user context, we don't really think of people following the recommended security practices as much as we think of people sharing passwords with friends and loved ones to make it easier to share information with them, or propping open electronically locked doors with garbage cans so it's easier to step out and sip some water and then come back in. And I sort of bring this up not to shame users. I think what they're doing makes total sense within the context in which they sit. But it does sort of speak to this disconnect between how security systems are designed today and how users end up wanting to use those security systems. And as we sort of enter this era of sort of pervasive physically embodied smart things, like smart locks and smart cars and networked medical implantable devices and things of that nature, where cybersecurity breaches start to have real physical security consequences, I think it's more important than ever that we sort of get this right and get users to not begrudgingly tolerate security, but actively engage with their security. And so I interviewed a few folks. I wanted to find out, for example, what makes people decide to use a PIN on their phone? What makes them finally decide to change their password after being reminded for the umpteenth time? Or more generally, what is the driving force behind a security decision, and what might we be missing? Now, I want to read you a few quotes from that interview. When I first had a smartphone, I didn't have a code, but then I started using one because everyone around me had a code, so I kind of felt a group pressure to also use a code. One of my boys wanted to use my phone for something, so I gave them my passcode, and not that I have anything that I don't care for them to see or anything, but after I did that, I changed it again. My friends have a lot of different accounts, the same as me, but they didn't get into any trouble. So I think maybe it will not be dangerous to reuse passwords. Anybody notice a trend? A lot of it is social. And it turns out that security behaviors, like any human behaviors, is largely driven by social trends, as illustrated by this candid camera clip, where the 3 people facing away from the camera are Confederates, and the protagonist will eventually give in to the group pressure and turn to face the wrong way himself. Now, out of the over 100 security behaviors that ended up being discussed in this interview process, around 50% of the discussed security behavior changes were the result of a conversation with or an interaction with somebody else. And so the social component is clearly very important, and yet traditionally when we think about security, we think of it as sort of a technology or an algorithm problem. So we try to create stronger crypto protocols. We try to create systems that formally verify the correctness of code, all of which is, of course, really important, and we wouldn't be where we are today without it. But it doesn't address the social problem, and so improvements in that end is not necessarily going to get more users excited about security. Even usable security, which expands the problem definition to consider security a problem at the human interaction level, typically considers it at the interaction level of the individual. And so we look at problems like how can we make authentication faster, encryption easier. But if my interviews are any indication, absent a more holistic knowledge of how security behaviors affect, sort of have social consequences, as well as sort of the social or the security consequences of social behaviors, we have little hope of doing much better than what we currently have. Now, fortunately, we don't have to start from ground zero. There's a vast body of social psychology literature that can sort of guide our understanding of how social influences affect security behaviors. Social psychologists have been, for decades, using these simple principles to get people to do things that are not immediately gratifying. Things like getting young children to engage with their phobias. Things like getting hotel guests to reuse towels and homeowners to be more energy conscious. It's just that relatively few of these ideas have cross-pollinated with security. And that's sort of where my work comes in. In my work, I bridge this gap between social psychology and cybersecurity by sort of creating new cybersecurity systems that are sort of more socially intelligent. And I do this in two ways. In sort of one thrust of my work, I draw on data science and computational social science to empirically model human social behaviors, in particular as they intersect with cybersecurity. And in the second thrust of my work, I sort of use these models to sort of guide the building of novel end-user-facing security systems that are more socially intelligent. Now today, I want to share with you 3 research projects that illustrate my research process in my quest to make security more social. And by the end of it all, I hope to have convinced you of the following 3 things. First, that social influence strongly affects security behaviors and that the design of a security tool affects its potential for social spread. Second, that social influence can be used to improve the awareness and adoption of existing security systems today. And then finally, that there's this huge opportunity to reshape much of end-user-facing security to be more social by design. So let's start with that first one, measuring social influence in security. Now, of course, the first step in making security more social is to understand how social influences affect security in the first place. And so I wanted to start with a simple question, which is, what, if any, effect does social influence have on the adoption of security tools? Now, this is a simple question, but historically has been very difficult to answer because we just haven't had the data. You know, that Jeff and James both use two-factor authentication have never been relatable facts, and certainly not overlaid on top of the fact that they're friends or they're both faculty at UW. I was fortunate to partner with one of the few corporations that actually does have this data, with Facebook. And at Facebook, I was able to analyze how the adoption of security tools, of optional security tools, sort of diffused through the social networks of 1.5 million people. Now, the 3 security systems that I studied were login notifications, which sends you notifications whenever sort of your account is logged into under suspicious circumstances, such as if you're logging in from a country you've never been to before. Login approvals, which is Facebook's version of two-factor authentication, where you have to enter a random code in addition to your password whenever you log in. And then finally, trusted contacts, which I would categorize as, you know, kind of social if the other 2 are standard. With trusted contacts, you enlist 3 to 5 of your friends to vouch for you in case you ever lose access to your account. So I started by randomly sampling 750,000 people who newly adopted one of those 3 security tools, as well as 750,000 so-called use-nots, or people who had never adopted one of those security tools. And of course, I balanced it over the 3 different security tools so that it was 250K users and use-nots for each of the 3. And then when I had this data, my question really boiled down to, can I distinguish between who are the users and who are the use-nots based on the presence of social influence in their networks? And to get at that, I borrowed a method from the social network analysis literature called match propensity sampling analysis, which helps us sort of distinguish between homophily and social influence. And for those less familiar with that terminology, consider the observations that, you know, Franzi uses two-factor authentication. And again, Jeff, I'm sorry, I'm picking on you again. Jeff uses two-factor authentication. And Franzi and Jeff are friends. Homophily would suggest that Franzi and Jeff are similar sorts of people. They're both faculty here at UW-CSE. And so they may have independently come to the realization that they wanted two-factor authentication on their Facebook accounts. Social influence, on the other hand, would suggest that one of them started using it first and influenced the other to use that, maybe because they recommended it, or maybe because one sort of saw the other person using it and thought it was a good idea. Now, if you use a correlational analysis like regression, you sort of risk confounding both of these observations for both of these explanations for those three observations. But match propensity sampling analysis tries to be a little bit smarter about it, and here's sort of how it works at a very high level. First, you pick a variable that represents social influence. In our case, this is easy. It's the percent of your friends who use a particular security system that you're trying to study. Then what you do is you discretize that variable such that you split the population into sort of equal subpopulations. So, for example, you get 20% at E1, E2, E3, and E4, and 20% who are not exposed at any level. And then you can say things like, somebody who has 3% of her friends who use login notifications is exposed at E1, but she's not exposed at E2 because she doesn't have at least 7.3% of her friends who use login notifications. And somebody who has, let's say 11% of his friends who use login notifications is exposed at E1, E2, and E3, but not quite at E4. Now, once you have those levels, for each of those levels, what you do is you look through your population, you find pairs of people who are very similar to each other, but where one is exposed at that level and the other is not. So for example, we might pair together Alice and David because they're both similar people. They're both young, maybe they're both pretty active on Facebook, and maybe they both have similar sorts of friends on Facebook. But Alice does have 5% of her friends who use login notifications, and David does not. Same with Bob and Eve. Very similar people, but Bob does have 5% of his friends who use login notifications, and Eve does not. And same with Carlos and Fred. Now, this pairing process is sort of where this magic of controlling for homophily happens, because now you have these two populations of people who are otherwise very similar, where the only sort of difference between those two groups of people is that one group has sort of this presence of social influence and the other does not. And then you can calculate the effect of social influence by comparing the relative adoption rate of the exposed group of people versus the unexposed group of people. So imagine if you had this graph where the y-axis is that aforementioned exposed minus unexposed adoption rate, and the x-axis is your different sort of discrete subpopulations of people that I mentioned in the first step. If social influence had absolutely no effect, you'd expect to sort of see this flat line at 0, because the relative adoption rate of the exposed and the unexposed are sort of indistinguishable, so their difference is 0. If social influence had like a constant effect, and it didn't matter if you had 10 friends who use login notifications or 400 friends who use login notifications, you'd expect to see sort of a flat line at some number. Like in this case, it's 25%, which means that the exposed are 25% more likely than the unexposed to use login notifications. But more likely, you would see something like this. This is what sort of the social psychology literature would suggest, which is that social influence will have an increasingly positive effect. If you see a lot more people around you do something, you're more likely to be influenced to do that thing yourself. So this is what you would expect. Yeah, what's up?
How careful do you have to be about this pairing to make this legitimate? It has to be something better than random pairing, or how does it?
Yeah. I didn't actually get into the pairing process, but what I use is a combination of demographic variables that were available at Facebook, behavioral variables, so how active they were on Facebook, how often they posted, how often they commented on what they posted and commented, as well as social network variables, which is things like how young are their friends, how sort of diverse are their friends, or how active are their friends. And then you sort of use those as independent variables, and then you sort of use a logistic regression to calculate a propensity score for people who are users and are use-nots, and then you find people who have similar propensity scores, but where one actually is a user and one actually is a use-not. So that's how the pairing process roughly works. Okay, so this is what you would expect to see if you have sort of what social psychology would predict. So what do we actually see? Well, starting with that graph again, if we plot sort of the effect for trusted contacts, you see pretty much the expected effect. Social influence has a positive influence, and it's increasingly positive as you have more exposure to friends who use that particular feature, which is great. This is some of the first empirical evidence that we have that social influence actually affects the adoption of security features, which is awesome. But once you start to plot the graph for login approvals, you see something very different and very weird. That red area of the graph is where the unexposed are more likely than the exposed to adopt one of the promoted security or one of the studied security features. So that means that social influence has a negative effect on the adoption of login approvals until the highest level of exposure we studied, which again was empirically determined, where that negative effect flips to a positive effect. And for login notifications, it's always negative, even at the highest level of exposure that we tested. And that's really weird and kind of flies in the face of what you would predict from standard social psychology theory, because you would predict something that looks much more like the trusted contacts curve. So what's going on there? Well, after speaking with some friends in social psychology and in marketing, it turns out that there might be a precedent for this, and it's this term called disaffiliation. And this pretty much spells the death of a product. It happens when uncool user groups start using your product. So, for example, when parents started using Facebook, teenagers started flocking off the platform in droves. Now, I want you to think about, in your head, the first person in your social network who used two-factor authentication on Facebook. Does it look like this guy? Now, it turns out that the early adopters of security features are usually people who are either experts at security or people who others perceive as having something to hide. So actual literal quotes from my literature and other literature show regular people calling security experts paranoid, nutty, or too expert, or something of that nature. So there might be this disaffiliation effect that occurs where the early adopters of security features tend to sort of put this stigma around security features as like you only use encryption, you only encrypt an email about lunch if you have something to hide, right? Like who are you trying to hide from? And this could sort of explain, this could be one of the explanations for why, even though we've innovated on usable security for upwards of a decade, security features almost never go viral, right? They always stay sort of clustered within the early adopter or the security expert network. There are a couple of pieces of good news, though. The first is that all of these lines go up and to the right, which means that there's a positive main effect of exposure. That means that, for login approvals, we can even see that that negative effect flips to a positive effect at high levels of exposure. It's just that relatively few people have that many friends who use login approvals. And for login notifications, it seems, at least in theory, that that line will flip from negative to positive. It's just that even at the highest level of exposure we tested, it hadn't flipped yet. Now, the second piece of good news is that the design of a security tool affects its potential for social spread. Trusted Contacts was not negatively affected by that disaffiliation effect. And after speaking with the people who designed that tool, as well as the people who use that tool, it appears to boil down to this idea of the tool being more social, which can be sort of further boiled down into these three dimensions. Observability. So when you use Trusted Contacts, you have to specify 3 to 5 of your friends to be your trusted contacts. And when you do that, they get a notification that that tool even exists. Whereas if you do login approvals or login notifications, nobody else in your friend network necessarily knows that that tool exists or that you're using it. The second is inclusivity, which is this idea that you're basically including your friends in the process of providing your own security. And then the third is stewardship, which is this idea that you're allowing your friends to act on behalf of your security in times when you can't really act on it yourself. And so these three design dimensions, if we can sort of replicate them in other security features, maybe we can translate them to have more of the sort of curve that you see for trusted contacts rather than for login approvals or login notifications. So to recap, social influence appears to strongly affect security behaviors, and the design of a security tool appears to affect its potential for social spread. But next I wanted to sort of drill a little bit deeper into that finding that I talked about at the end over there, which is, can we increase the awareness and adoption of existing security tools by making them more social? Now, it's hard to make login approvals or login notifications more inclusive or more stewarded, but you can definitely make it more observable if, for example, you show people notifications that some number of their friends are using that feature, for example, right? So that's exactly sort of what I wanted to evaluate next. I basically wanted to run a controlled randomized experiment with 50,000 Facebook users. And I was able to do this as sort of part of an annual security awareness campaign that Facebook was running anyway, where they were trying to promote the use of optional security tools that most people didn't know about. Now, the basic premise was simple. Show people a simple notification on top of their newsfeed that extra security tools existed for them to protect their accounts. And before I came in there, it was a very vanilla announcement. It was just, you can use security settings to protect your account. And then there was a call to action button, which, if clicked, would take users to an interface that would give them information about the promoted security tools, as well as allow them to enable those security tools. I came in and added this concept of observability, or social proof, as as it's known in the social psychology literature. And basically, I tested 7 different presentations of this social proof. So all the way from sort of a specific presentation in the raw number condition, where I just actually calculated the number of their friends who used a particular security tool, and I made that information available to them at the beginning of the notification. 108 of your friends use extra security settings. You can too. All the way to a more vague notion of social proof in the bottom right over there, where you can see some of your friends are using extra security settings, and you can also protect yourself. Now, so these were 7 sort of different presentations of social proof. And in addition to that vanilla control condition, I basically had 8 conditions to which I randomly assigned my 50,000 participant sample. So that resulted in about 6,250 participants per condition. And I ran this experiment for about 3 days. So if any of my participants logged in that 3-day period, they would have seen the notification to which they were assigned. Now, to evaluate the efficacy of these different notifications, I calculated the click-through rate, the 7-day adoptions of the promoted security tools, as well as the 5-month adoptions of one of the promoted security tools to see if there was a difference between the short and long-term effects. And this is what that data roughly looked like. So 93%.
There's a total detail, but whether they were in at the end of the period or if they ever went in during the period. I mean, some people might sign up for something and then get sick of it, or you know.
It was whether they were ever in. Yeah. So I didn't necessarily track drop-offs. Although that would have been implicitly baked into the 5-month calculation because I just did another count of who was using it. So 93% logged in and saw one of the announcements. 13% clicked on one of the announcements. 4% adopted one of the promoted security tools in 7 days. And about 10% in 5 months. Now, here's what those numbers look like broken down across conditions. And there are a couple of quick things to glean over here. Sorry, Jeff, I know I'm not supposed to use a stacked bar plot, but I'm going to do it anyway. So the best so the best condition. So basically, all of the social observability conditions improve click-through rate relative to control. And the best conditions even improve click-through rate by 1.36x, which is pretty significant. If you've ever done an A/B test on like 1-sentence copy at this scale, you'll know that a pretty good result is to get like 5% improvements. But a 1.36x improvement is very substantial and very huge, so that was kind of cool. The second thing to glean from this is that the best 2 conditions even improved adoption relative to control. So this was particularly significant because the social proof was only in that first sentence of that notification. As soon as they clicked on the call to action button, the social proof disappeared. And so we were getting 10% more people who actually used one of those security tools just from sort of adding one simple sentence at the beginning of that notification, which gave them some idea that their friends also used those particular security tools. And taken together, that's some pretty significant evidence that, you know, by increasing the observability of security tool usage, you can also sort of increase the awareness and adoption of these security tools, which was a result that was simple and strong enough that it's kind of changed the way Facebook promotes these tools and even designed some of their new security tools. So that was kind of cool. All right. So social influence can be used to improve the awareness and adoption of existing security systems and behaviors. But retrofitting social sensibilities onto existing security systems can really only work to a certain extent, right? Like, you can't really make login notifications and login approvals more inclusive or stewarded, which are 2 of the other design dimensions that sort of made security tools more social. So next, I want to talk to you about a more long-term vision I have to sort of recreate some end-user-facing security experiences to be more social from the ground up. And as sort of an example of what I mean by that, I want to present to you Thumbprint, which is a socially inclusive local group authenticator through shared secret knocks. Now, in a nutshell, with Thumbprint, group members agree on a shared secret knock that they tap onto an instrumented sensor surface. And this secret knock can be sort of any small solid token tapped in a certain way. And as the video shows, after registration, if groups enter the correct secret knock, they're granted access. And if they enter the wrong secret knock, they're rejected access. But I want to emphasize here that the cool part about Thumbprint is not necessarily the interaction modality. It's the fact that you only need a single shared secret knock to not only authenticate a group, but identify each individual member of the group. So group members don't need to keep secrets from one another. And this might be a useful property for a wide spectrum of small local groups who sort of collectively own and share low-stakes group resources, but as my advisors put it, only need enough security to keep bozos from poking around where they're not welcome. And this could be groups like families who share game consoles and smart appliances, like smart toasters or whatever. Work teams who share kitchenettes and meeting rooms with snacks, and they want to make sure that other competing work teams aren't getting into their snacks to fuel themselves. As well as classrooms of students who share like tablets or chemical beakers or whatever classrooms of students share these days. I mean, the whole plot of Breaking Bad wouldn't have happened if they had Thumbprint, because the administrators would have known that Heisenberg was the one who stole all of the chemical beakers. So this is important stuff. For these groups, divisive authentication that requires individual secrets is often inappropriate because it creates unnecessary social friction. Like imagine families trying to keep their own individual secrets from one another to access like a Nest thermostat or something like that. And it also creates this weird property where security is only as strong as your weakest link. It's only as strong as the person investing the least amount of effort and time into the security of the group. On the flip side, having a shared password or a PIN is also often not great because it precludes things like personalization. Everything's getting personalized these days, but in order to personalize, you first need to know who to personalize to. It also precludes things like parental controls. For example, for a shared tablet that parents share with their kids, and they don't want them to rack up costs on the App Store. And it also precludes things like audit logs. So Thumbprint kind of sits in the middle of these two things and provides both inclusivity in that it only requires a single shared secret, but it also provides identifiability in that you can still distinguish between each individual member who knows the secret because everybody mechanically expresses it a little bit different. So how does that work? Well, at a high level, Thumbprint works by people entering their secret knock on a sensor instrumented with the accelerometer and a microphone. So every time they do that, it generates acoustic and acceleration streams, which I extract a bunch of time and frequency domain features from. And then I run both supervised and unsupervised machine learning on those individual feature vectors in order to understand not only the group shared thumbprint, but also the individual expressions of the thumbprint. And then finally, it can regulate access control through whatever endpoint you want. In the video I showed, it was a laptop, but it could also be an electronic smart lock. And this all happens in 3 phases. In the registration phase, each group member basically is required to enter the shared secret knock 10 times. And this is to seed Thumbprint with enough data to learn how everybody expresses a thumbprint and how everybody does it slightly differently. Now, every time they enter the thumbprint, it creates these acceleration and acoustic streams from which I extract dozens and dozens of features on both the time and the frequency domain. And this is all standard DSP that I'm using. I'm certainly not doing anything fancy or special over here. But basically, the result is you have these feature vectors that are dozens of sort of columns wide, but relatively low in terms of the number of rows because you only have 10 data points per person. So the first step in sort of creating a classifier to distinguish between individuals is to sort of run this through a supervised feature subset selection algorithm. The one that I use is correlation feature selection in order to find a parsimonious subset of the features that are important to best distinguish between the individual users and the individual group members of the group. And so at the end of that, you might have a graph that looks something like this, where if you have 2 particularly discriminatory features, fx and fy, and each one of those points over there is an individual sort of training attempt or registration attempt by one of the group members, you might see something that looks like this, where it's like nicely separated in feature space. Of course, in practice, it's never that nice, but this is an abstraction. Next, I run a semi-supervised clustering algorithm at a per individual basis in order to sort of understand these individual different expressions of the thumbprint in the feature space that I've selected. And importantly, I do this at a per individual basis. And this is because, just imagine, the first time you enter a thumbprint might be very different than like the nth time you enter a thumbprint. And this allows, like, clustering at a per individual basis allows us to keep each cluster internally coherent, so it all represents data from one user. But it also allows us to model drift, so people, who learn how to enter the thumbprint differently over time, that can be captured. But also, the way I enter my thumbprint before my morning coffee and after my morning coffee might be slightly different. And so this could also capture nuance and variation like that. And now once you have these learned clusters, authentication becomes a matter of comparing an unlabeled attempt in feature space to sort of the cluster centroids of the learned expressions. And we call this the feature vector difference over here. And then you can compare that difference against a configurable threshold. And if it's close enough to one of the cluster centroids, you'll authenticate. But if it's far, then you don't authenticate. And so in this case, the user would not be authenticated because it's not close enough to any one of those cluster centroids. So roughly, that's how Thumbprint works. But to figure out if it actually works, I wanted to boil that question down into 3 other questions. First, can individual group members entering their same thumbprint be distinguished? Now that's important because that's one of the pitches of Thumbprint, right? Like you only need one single secret in order to distinguish between each individual member. Can people enter their thumbprints consistently after time-separated session? If I register my thumbprint today, am I entering it the same way if I do it tomorrow? And then finally, can casual but motivated adversaries be detected? Again, I'm not designing Thumbprint to be perfectly secure over here. It's meant for low-stakes use cases. But it's still built as an authentication system. And so it'd be nice if somebody couldn't just randomly enter whatever they wanted and be granted access. So to answer these questions, I ran sort of a 2-day in-lab study with 3 groups of 5 participants. Basically, on the first day, participants agreed upon a shared secret. And they were allowed to sort of view the video of the shared secret as many times as they wanted. And when they were ready, they each entered 10 registration attempts of the thumbprint in the first day. In the second day, participants came back individually. And the first thing they were told to do is to replicate the thumbprint that they had learned the previous day. So the group shared thumbprint they learned the previous day. But they were given no memory cues. They had to do it entirely from memory. And once they'd done that, they're then asked to break other groups' thumbprints as one of 4 different adversaries. The token-only adversary was given the correct small solid token attack, but had to reconstruct sort of the pattern themselves. The sound-only adversary was given an audio file of the group shared thumbprint, but was not told what token to use or what the pattern was. The video plus wrong token adversary was given sort of a video file from the over-the-shoulder perspective of the group shared thumbprint, but was not allowed to use the correct token. And the video correct token adversary, of course, was allowed to use all 3. So I trained Thumbprint on data collected for each group on the first day, and then I tested it on data collected on the second day. So this was, for the authentic attempts, this was 24 hours later, and for the adversarial attempts, this was from people who weren't part of the group. And so this graph kind of shows the performance of Thumbprint based on those parameters. Now, the y-axis here is the mean feature vector difference. So this is how far in feature space from those cluster centroids I talked about before. And so lower is better. Lower means you're closer to one of those cluster centroids. And the x-axis over here is the different types of users. So immediately you can see that the correct member has a far lower mean feature vector difference, even 24 hours later, than all of these different kinds of casual but motivated adversaries that we tested. And if you sort of put that configurable threshold at slightly above the mean feature vector difference for the correct member, you can get an equal error rate of approximately 12% with a misidentification rate of less than 5%, which is good. It's comparable to other behavioral biometric authenticators out there, like keystroke dynamics, which was widely publicized or widely published and cited. That has approximately an equal error rate of 13 to 14%. But of course, again, this is meant for low-stakes cases. You're not going to be wanting to put anything that you really need to be secured behind Thumbprint. But it does sort of point to this fact that we can get sort of the performance that we want from accepted systems, like keystroke dynamics, but still add the social dimension and still not really compromise anything. So can individual group members entering the same thumbprint be distinguished? The answer is yes, but I also want to remind you that I only had 10 data points per individual. And so as we get more and more data points from a real deployment of Thumbprint, which would be over weeks and months, you might have hundreds of data points on which you can run much more sophisticated machine learning algorithms like one-class classifiers and anomaly detection algorithms. And so I expect that this performance would get better with even more data. Can people enter their thumbprints consistently after time-separated sessions? The answer is again yes, and again I expect the performance will improve with slightly more data. And then can casual but motivated adversaries be detected? The answer is mostly, again, a very motivated adversary with better technical skills is probably going to be able to break Thumbprint, but it's not meant for perfect security. It's meant for good enough security with the added dimension of being social. But again, I expect this, the detection of adversaries should get better with more data. So to recap, I presented 3 projects. The first was an empirical analysis of how security behaviors kind of diffuse through social networks. And I found that social influence strongly affects security behaviors, and that the design of a security tool affects its potential for social spread. In the second project, I've sort of presented an experiment of sort of increasing the observability of these security tool usages, and found that we can improve the awareness and adoption of existing security systems through these simple social psychological interventions. And then finally, I presented Thumbprint, which is sort of a pointer to this larger vision that I have of sort of reshaping the future of end-user-facing security systems to be more social by design. And while Thumbprint is certainly a promising first step towards this vision of socially intelligent cybersecurity, it really is just a first step. More generally, I want to build on this momentum of sort of laying out this foundation for social cybersecurity and create a suite of cybersecurity systems that emphasize these dimensions of observability, inclusivity, and stewardship. Now, by creating more observable security systems, what I'm really talking about is engaging with this question of how can we make it easier for people to observe and emulate good security behaviors. Now, in the physical world, we can sort of see threats that are coming at us that sort of threaten our physical safety. And we can see sort of what everybody else around us is doing to protect themselves. For example, if a tornado is touching down, we can see that it's touching down. We can know, to probably avoid that. And we can see what everybody else is doing in order to protect themselves from that tornado, hiding under a desk or whatever. But in the virtual world, we're sort of in a fog of war. We can't see what threats are coming towards us. We can't see what anybody else around us is doing to protect themselves against those threats. So it's really no surprise that end users are often not thinking about security. It's just not something that's very salient. So how can we change that? To make security more inclusive, I'm really interested in engaging with this question of how can we design additive security systems that make group security a sum function instead of a min function? Now, in the physical world, when you put 2 people together, there's a sense that you're safer together than you are apart in most cases. In the virtual world, however, that's absolutely not true. If I'm, for example, sending confidential information to somebody else who has weaker security behaviors, then I've effectively declassified that information because it's only as strong as that person's security behaviors at that point. So it creates this weird structure where security in a group is only as strong as the person who has the weakest security in that group. But what would it look like if we made cybersecurity a little bit more like physical security, where when you put people together, there's a sense that you have more physical safety as opposed to less physical safety? And then finally, to make security more stewarded, I'm really interested in engaging with this question of how can we design systems that allow people to act on their concerns for their friends and loved ones? Again, to use a crude physical world analog, I can offer my friend a ride home at night if I think that it's dangerous for that person to be walking alone. It's easy for me to offer. It's easy for them to take me up on that offer. But in the virtual world, I can know that 1 billion Yahoo accounts got hacked, and I can know that my mom has a Yahoo account. But short of calling her up and nagging at her, there's really not much I can do. And there's no reasonable expectation for me that she's actually taking that advice. So how can we sort of make it easier for people to act on their concern for others? But more generally, remember that I started this talk with this larger question of how can we design systems that encourage better cybersecurity behaviors? I think social is promising, and it's one that I've invested a lot of time into and one that I plan to invest some more time into, but it's certainly not the only way. In my PhD, I've tackled multiple different ways of answering this question. And in fact, the best ideas I've had have come from talking with people who are very different from me in order to sort of understand how to approach this problem more holistically, and then talking with sort of the makers and builders who are more similar to me to figure out how to operationalize those ideas into something real. And so to that end, I'm really looking forward to sort of synthesizing collaborations with the modelers, the theorists, the builders, the makers, the hackers here at UW and elsewhere. And I really look forward to hearing your perspective on how I can approach this problem better. Now, of course, I couldn't have done any of this work without the support of my advisors, my committee, my mentors, and the many people that have sort of tolerated me over the past 6 years. Thank you for listening.
Yeah. A really interesting talk. I had a very different reaction to the problems that you mentioned, which probably stems from my background as an AI researcher. It seems like instead of making security more social and having us be more involved, we really want to have the computers be smarter so that it's less work for us to do this. And if they're watching, a lot about what we're doing and they've had the same kind of sensing capabilities that we have, then it seems like it'd be much harder to fool them into letting somebody else have access to materials that they don't like. So what's your reaction to that thought?
I don't think they're mutually exclusive. There's a whole line of, there was kind of a whole line of research in usable security that was trying to automate security, so to remove the human in the loop completely. But there was a lot of pushback against that just because I think we can all assume that systems fail every once in a while. And if systems fail, and security systems are all about dealing with exceptions rather than rules, it is really difficult for users to sort of react to that failure. And then it creates this system where people just either totally ignore very important security warnings because it's completely out of their minds at that point. And it can also potentially sort of lead to these scenarios where, because security is more about dealing with exceptions rather than rules, that people are trying to, when people encounter these system failures, they don't know how to react, so they totally disable the automation if that's a possibility for them altogether. And so the trend in usable security has not been so much to remove the human in the loop, but rather to make it easier for the human in the loop to sort of interact with these sort of exceptional cases. Now, you might argue that it's worth revisiting because machine learning and AI has, of course, gotten a lot more sort of active in the more recent years since this getting rid of automation in security was sort of the trend. But I would say it's not mutually exclusive, which is my original point. You can, for example, imagine having agents that are sort of these intelligent systems that you're talking about, like interactive agents, sort of like Jarvis and Iron Man, who's never asking Iron Man for a password, but who's still interacting with the user and letting them know in like human interactable words or language that this is a thing that the agent is doing and that the user should be aware of the things that are being done. So that could be one way of getting sort of the best of both worlds.
So I think an interesting concern that's shared with a lot of social computing is just basically access to people and their behaviors. And so I was just curious, as part of your future research agenda, if you could say more, what are the prospects for doing this sort of social influence-oriented security work outside of the realm of proprietary corporate held data?
Good question. So I'm sort of at this space right now where I've created a lot of sort of the theoretical foundation for what I think will be my social cybersecurity systems work for a while. So maybe I can escape that or deflect that question by saying that a lot of what I intend to do in my future work with social cybersecurity is to build on these design dimensions of observability, inclusivity, and stewardship in order to sort of create these systems. And tech transfer would be great, but it's not contingent upon being able to deploy whatever I deploy to Facebook in order to evaluate it, for example. More generally, though, that's just a broader problem in social computing in general, which is how can we actually evaluate how interventions affect communities rather than individuals, because that takes much longer and there are much more sort of degrees of freedom to control. I don't have a good answer, but yeah. Oh, blue hoodie, or sure.
You mentioned disaffiliation, but if I understood correctly, that was in the context of tools that lacked observability. So how can you have disaffiliation without observing that others, like people I want to be disaffiliated with, are using that tool?
Yeah. So disaffiliation could come into play when those conversations are happening. So I'll say this. There appears to be an effective social influence because the only difference between those two groups based on sort of this pairing process should be that they have friends that are doing this or not. So as sort of given that there's this social influence going on, I don't know what the mechanism of the social influence is. You can sort of envision that when those interactions are happening, the only people who are using those security tools in the early adopter phase of the network is people who are like paranoid or people who are experts or something of that nature. It's only once you have, one of the things I didn't get into in my talk was when you have sort of people from different communities within your social network, so if you have like a high school friend, a college friend, and a graduate school friend, as opposed to 3 high school friends who use that particular security tool, and that can also sort of overcome this disaffiliation effect, because you can't ascribe the properties of any one group of people to the security feature itself. So those are sort of the 2 data points that I point to in the paper as dealing with that problem, but it's not perfect. Yeah.
Do you have any thoughts about how to square this disaffiliation problem due to people seeing experts as being paranoid with this motivation towards stewardship that you talked about later? So if experts feel some obligation to try to spread the word and help people, but that's actually having potentially a negative effect. How do you square these things?
Well, so one is sort of passive nagging, and the other is sort of like actively being a steward and like actually working towards the benefit of somebody else. So there's a slight interaction difference between me just yelling at my mom and telling her, change your password now, and doing that like every day until she actually does it, to a potential stewarded system where I can sort of make the process of her changing her password easier for her to do, or potentially do it on her behalf in some capacity. I don't know what that system will necessarily look like. I do have ideas, but that's generally how I'm thinking about it. There's a difference between sort of this, and in fact, experts are kind of disincentivized from sharing that information right now because they are viewed as paranoid and nutty. But if they can actually act and people can actually see the benefits of that interaction, then maybe we can square those away. But that is a good question.
I was curious in your work when you were talking about the social influence of Facebook. If Facebook, or if you would consider lying, where you tell people that 50 of your friends use 2-factor even though only 2 do, and what your thoughts are on using mechanisms to fake social influence instead of actually relying on the social network.
It would be nice, but Facebook is very against deception, as you can imagine, after the emotional contagion study and all of those things happened. This is one thing that we were considering doing outside of Facebook in order to better evaluate the effect of the number. Now, it turns out when you have 50,000 people, you can get like a good spread of those numbers anyway. And so I did actually do an analysis of how that number affects people's click-through rate, and that has a very significant effect. I just didn't get into it here. So in theory, you can actually test these different numbers. I only tested it linearly. I didn't test it at like different levels like I did with the first study, but there was a strong linear correlation. Yeah.
Is there a particular reason why you chose this sound-based system for the modality of the password in Thumbprint? And is there a reason for that, or are there other modalities of this type of thing that would work better or worse, or why?
Yeah. So I'll answer that in a couple of ways. One is the more high-level way, which is that Thumbprint is just meant to be sort of an initial exploration of the design space, and is not meant to be the final form factor of social cybersecurity systems. Now, the inspiration for Thumbprint was when I was looking for a group, offline group analogs for authentication. And one of the things that came across that we could actually create with modern sensing technologies was this idea of secret knocks during the Prohibition era. During the Prohibition era, of course, people were using secret knocks in order to get into bars and authenticate themselves as somebody who was in the know. And that secret knock spread through social channels. And so it seemed like a nice sort of translation onto the sort of thing that I was trying to create. But of course, you could imagine you could also have this like same secret but distinguishability property from keystroke dynamics. But you need a lot more data for it. So there might be other potential modalities for the same sort of thing that Thumbprint accomplishes.
So in that space, for example, that may be much more, the Thumbprint sounds may be much more observable to somebody who's in the room with me, for example, than keystrokes would be. And I was wondering whether that was something you wanted or didn't want.
That was something I wanted, but it wasn't something I explicitly evaluated, so I didn't bring it up. I'm pitching Thumbprint more as an inclusive system, but there is this observability component to it. And ideally, you would create systems that have all three, the observability, inclusivity, and stewardship. Yeah.
So in a way related to Maya's question earlier, which is how did you arrive at the idea of the social factor being so important in the first place? You know, you talked about at the beginning on Facebook, there are the users who use the certain things and the users who don't use them, and you came in with the hypothesis that that was due to these social effects, but presumably there are other hypotheses you could have had. So I'm just curious how you arrived at that, or whether you tested others as well.
Yeah. Well, I thought I tried to get a little bit at that with the initial part of my talk. It was the interview study, where social factors appear to be very strongly influential, but I couldn't find too much literature that actually dug deeper into that, because, you know, it's pretty difficult to actually empirically test the effect of social influence if you don't have sort of the proprietary data nest that Facebook has. So the hypothesis generation was from that initial sort of work, trying to figure out what's the driving decision factor behind security decisions.
Were there other things that you saw in those interviews that might be interesting?
Yeah, we should maybe talk about that a little bit more. I can't remember off the top of my head, but a lot of them were people could not articulate why. They were just like, I just got to do this. And, you know, maybe that is because of some social thing, but I didn't necessarily classify that as a social reason. Yeah. But, you know, some of them it was easier to do it, and, you know, that wasn't an interesting result, so I don't talk about that here. Yeah.
So you talked about inclusive security systems where when you add more people, it's safer, like the physical world. But it seems like there's sort of a fundamental difference between like physical force and information confidentiality, where like by definition, the more people that know a piece of information, like the more weak links there are. So do you think, are there limits to the type of data or systems that can be secured in an inclusive way, or is it sort of a universally applicable?
Yeah, that's a good question. So I think there are generally like sort of two ways to make security more social. The first way is through sort of artificial sociality, as in my experiment, which I think is more generally applicable. And maybe, I don't know if there are inclusive or stewarded ways to do that, but maybe there might be. For example, like somebody sending you the notification more personally or something of that nature. But the other way is to actually create these new systems that are more inclusive or stewarded. For that, I don't really have a good sense for, you know, if you make things more inclusive, you necessarily make it more sort of weak links, because it could be that everybody has the same thing, and so there are no weak links by kind of definition when there's no individual sort of secret creation process. But, you know, this is fairly early in the exploration of the design space. I don't want to have any sort of like, you know, total answers to that question, but yeah.
In Thumbprint, did you look at all of like finding the group and I know it's someone else's token or they're using the tag? And I like try to authenticate as them. Like confused through your identification process in that way.
Yeah, so that's a pretty great point. So the adversary model in Thumbprint is that everybody in the group kind of trusts each other. So I didn't look at that, although I am running a field investigation at Thumbprint where I'm actually deploying this with real groups, and I'll see if that pops up at any time during the evaluation of that. I don't have the data for that right now, but we'll see. I mean, of course, the misidentification rate was not 0, so presumably this is going to happen every once in a while.
One last question, if anybody has one.
For Thumbprint, was that misidentification rate correlated with the number of users using it? I'm wondering if you get more and more users, whether they'll saturate the feature space in a way that it becomes easier to match.
Yeah, hard to say because I limited it to 5 members per group. So, you know, to some extent, you would imagine that would be the case. But if you have more users, you also have more rows, and so you can have more features, and so you can expand the feature space more. So there'd be sort of, like, that could be the case. It also could be that if you expand the dimensionality of the feature space with the more data you get from the more users, you wouldn't run into that issue. But
Okay, thank you.